Can you hear me? So it's a pleasure to announce the next speaker, Lepowsky, Rutgers University, who will talk about automated proofs of generalized Rogers-Ramanujan identities.
Thank you very much. Can you hear me okay?
Yes.
Great. I'm very happy to be here to honor Krishna. My nth time in Gainesville. I can't get in anymore. And I really love coming here, and Krishna's hospitality has a great deal to do with that. And which so many people mentioned, I too was fortunate to meet Krishna's father, and that was really special. Later, during the actual talk, I'll mention a certain important part of Krishna's work. My field of math is vertex operator algebra theory, and I'm not going to be technical in any way about that. I'll try to give a hand-waving, literally, roadmap of how the Rogers-Ramanujan identities and generalizations have stimulated the development of the theory itself, and are continuing to do that. That's the main theme. So, here's, for the purposes of this talk, this is some of what happened, starting in 1977, when Steve Milne and I collaborated to discover the product sides of the Rogers-Ramanujan identities from certain standard integrable highest weight modules for the affine Lie algebra SL2 path, also called A11. Then that led to the development of algebras of vertex operators, which had appeared in string. Vertex operators had been in string theory, but we weren't string theorists. We weren't, we weren't physicists, nor number theorists, nor combinatorial, nor partition theorists, at least me, Steve is. But we found that these things had to be invented to solve this philosophical problem, which I'll sketch a bit of. And then vertex operator algebra theory developed greatly because of the monstrous moonshine problem, which I won't say anything about, except that there are deep connections between the theory and many things. But one needs modules for algebras, and one needs relations among modules, intertwining operators among modules. It was very natural for those theories to be developed. Now, the motivated proof, unquote, approach to proving Rogers-Ramanujan type identities is currently stimulating or seeking new structure in the theory. So here's my slide on the Rogers-Ramanujan identities, and I don't have to leave this here for very long, except to say that, as I say at the bottom, the difference 2 condition on this in the sum sides, which I'm writing in words instead of Q-series form, that condition is invisible from the product sides. And it was a philosophical problem to motivate the sum sides from the product sides Andrews and Baxter's monthly article was, luckily I was and am a member of the MAA as well as the AMS, so I had that. And I looked at it because I wanted to see if the 2 Rogers-Ramanujan identities could be proved together in a natural way using vertex operator algebra theory, not separately as Robert Wilson and I had done. the nature of the motivated proof is that the first Rogers-Ramanujan product starts 1 plus q to the first plus q to the second, etc. The second one, g sub 2, starts 1 plus q squared, etc. If you subtract those and divide by q, you notice that it starts, the result starts 1 plus q cubed, etc. And that pattern persists. And Andrews and Baxter called the statement that the ith one of these iteratively defined formal series in Q is 1 plus something divisible by Q to the I. They call that the empirical hypothesis. And the idea is you can do this experiment and observe that this is happening. And then it turns out, if you prove the empirical hypothesis, you quickly get the sum size from the product size. I won't go into that. This talk won't have any details or formulas. The earlier motivation, a motivation for looking for such a proof is to figure out why the product side G sub 1 should dominate the product side G sub 2. It's as hard to prove that directly as it is to prove the Rogers-Ramanujan identities. And this motivated proof does that for free. The only boring part of the motivated proof is to verify the empirical hypothesis by postulating a closed form for G sub I and then proving it works.
And this is not any shorter than any of the other proofs?
No, this is not supposed to be shorter, but it's my favorite proof other than Robert Wilson's and mine, using budding vertex operator algebra theory, which was and is the longest known proof by a large factor. But this is my favorite classical proof because of my talk. So, and the word boring will disappear at the end. That's some new research going on. That proof is essentially the same as a Rogers-Ramanujan proof and as Baxter's proof when he rediscovered the Rogers-Ramanujan identities. Wilson and I developed vertex operators and what we call Z-algebras, which are certain algebras of very specifically constructed vertex operators. And we did it to try to find the difference to and more general conditions in these modules. The Rogers-Ramanujan identities for us didn't want to count partitions. They wanted to count the dimensions of subspaces of canonical structures. And that worked. Categorifying partitions is kind of, it's not a very good choice of wording, but that's kind of what I mean about counting partitions to looking at subspaces, or canonical spaces. But now we want to categorify the motivated proof. And that's an unsolved problem. But it's leading to lots of papers and lots of research. The operators that we constructed, we called Z operators because they centralize something, a certain subalgebra. And the nature of how the difference 2 condition arose was that we formed generating functions from vertex operator ideas. And the components of this Z of X generating function are Z operators such that when you apply them to the highest weight vector of this module, and you apply relations among the generating functions that we discovered for this purpose, you can straighten monomials in the Z's to get difference at least 2 between adjacent subscripts. So this is a long story, but one thing I'll add to this is that the relations are not commutation relations or even anti-commutation relations. They're what we call generalized commutation relations because they were new, and those kinds of relations turned out to be crucial in the as yet non-existent vertex operator algebra theory. That's an example of the interplay between these ideas. Okay, Stefano Caporelli was one of Robert Wilson's and my students in the 1980s, and Robert Wilson and I had done the case of all of the standard modules for SL2 hat, A11. And beyond the Rogers-Ramanujan identities, there were the Gordon-Andrews odd modulus identities and the family of Andrews-Rousseau even modulus identities. And it was a lot of technically tricky work, but it worked beautifully. So it's natural for our next student to do the next affine Lie algebra, called A22. Okay, 10 years later, he did the first case because it was hard. The very first case was Rogers-Ramanujan again. The second case was the new thing. And that brings me to the Krishna story. But first I'll tell it from my point of view. So I was invited to give a talk at the 1992 Rademacher Centenary Conference at Penn State. And Stefano Caporelli and I plotted, so to speak. Well, we decided since he couldn't prove his two identities, he could only prove one inequality with overwhelming numerical evidence. But the Z algebra theory was sound. He had a strong thesis. We decided that I would write this on the board. I mean, write the content of this on the board, and report on what vertex operators were doing or stuff in Z algebras in a non-technical way, much like I'm doing now, and say that whatever they are, this comes out as a conjecture. And one of three things could have happened. People like Andrews, Gordon, Rousseau were all there. Krishna wasn't there, but he was there in spirit, as I'll explain. We're either going to say, okay, that's nothing, we knew that, it was known a long time ago. Or they might have said, no, we didn't know that, but interesting, it's amusing you're doing some silly theory, but it's easy to prove. Or they could have said, we've never seen anything like that before. Where did it come from? Or rather, how can we invent new ideas to prove it? Number three happened. So George Andrews changed his talk in the conference to be a talk on a proof of Caporelli's conjecture. And then Krishna wrote his side of it, which was substantial, even though he wasn't physically there, in his memorial article for Basil Gordon in the AMS Notices. Let's see, since I don't have much time, I'll just refer you to that. But briefly, Gordon told Krishna about this, and they discussed the method of weighted words. And Krishna got a great idea, and Andrews and Alladi and Gordon collaborated on another proof of Caporelli's conjecture with a refinement. And that was very significant. Well, that took a lot of years. So 20, 30 years later, there aren't 30 years. 20 years later, Robert Wilson's most latest student, Deb Nandi, who is a nice postdoc in India now, was supposed to do the next level for A22. And it took many years, and he did it, but it's still only a conjecture. I won't put it here because it's longer. Drew Sills' talk is about Caporelli's and Nandi's conjecture/theorems, and his ideas on trying to understand them and place them into a classical context. So I'll refer you to his talk. Non-D's identities, the product sides are on Slater's list. But the sum sides, and I just checked with Drew today in Slater's paper, that the sum side has a product multiplying it. It's not a real sum side. So non-D sum side, as you'll see in Drew's talk, is weird, but it's canonical in terms of Z-algebra theory. Something new is going on in the vertex theory, and we don't know what it is. So I think motivated proofs will help us collectively understand what is really going on. I believe that something chaotic in some kind of technical sense is going on. Chaotic or wild. You're not supposed to go to the next level of an easy-seeming Lie algebra module. And it goes, just drives off a cliff. And who knows how many decades the next level will take. So Stefano Caprelli's thesis problem to do all of A22 was a little bit over-optimistic for Robert Wilson and me to make him do. But it all worked out well. Okay, now, the idea of motivated proofs includes mixing the two identities. And our Z-algebra theory does one identity at a time. In vertex operator algebra theory, one is supposed to mix modules. On that first preview slide, I mentioned intertwining operators among modules. And that's a very deep part of the whole theory. So the hope is to find an intertwining operator algebra explanation, unquote, of motivated proofs, which should hopefully be sufficiently canonical and powerful that it will give motivated proofs of Caprelli and Nandi and lots of others. That is unsolved. Drew Sills and I tried hard to invent a, quote, motivated proof of Caprelli's identities. We got some fascinating ideas, but we don't know how to finish it right now. But here's some practice. The Z-algebras I've been talking about are what are called twisted Z-algebras for a technical reason. There's also untwisted theory. And in Rogers' first paper, there was this Rogers-Ramanujan recursion, or one of his first papers. This was Rogers' first approach to proving the Rogers-Ramanujan identity in 1894. This is an XQ recursion. There's the extra variable X that you will know about. I didn't mention X yet until now. So it turns out there's a dictionary between this type of proof, which some of you know very much about, and the motivated proof. The dictionary is to specialize this X by all the positive powers of Q, all the non-negative powers of Q. And if you know a recursion of this type, and you know that an expression satisfies it that will fit with the ultimate product side of your identities, then you prove the identities. And if you have such a proof, that was what Rogers did, then if you specialize X to those powers of Q, you have generated a motivated proof. So there's a method of cheating. That's a technical term. If we want to practice learning how to invent motivated proofs, we can look at the Rogers-Selberg recursions chapters. It's not that. We look at chapter 7 of George's book on partitions. And we did that with the Rogers-Selberg recursions, but we hadn't invented the cheating method yet. So Min-Shen Zhu, a postdoc at Rutgers, and I constructed a, quote, motivated proof in the same spirit as the Andrews-Baxter proof that proved the odd modulus Gordon identities. And then that's where things stood for a while. Well, actually, I should say this first. Before that, Caparelli and Anton Milos and I categorified that untwisted recursion with the X and the Q in it. This is untwisted practice for constructing intertwining operator algebra theory to explain Rogers-Ramanujan type identities. The trouble with that is it didn't and doesn't yet have the product citing. But we learned a lot, and that program got developed greatly by my student Karina Kalinescu and Ijo Huang's and my student Chris Sadowski, his Anton Milos' student Michael Penn, Mirko Primitz, Buderotz, another student, Kanada. That this untwisted story has taken off. There are no product sites in it yet, but a lot is happening. We're collectively learning a lot. We want the twisted theory with no X in it. So that's what Min Shenju and I wanted to try to advance by looking for, which I accidentally said 3 minutes ago, looking for a quote motivated proof unquote of more identities. The most natural family is the odd modulus Gordon identities, and that worked. Okay, now I have to define some terminology in a subtle way. Motivated proof is a technical term, but the technical term has quotes around motivated proof. If you just say motivated proof, they'll say, oh, what's your motivation? No, motivated proof with quotes. So, quote, quote, motivated proof, unquote, has now become a technical term. So has quote empirical hypothesis, which doesn't need double quotes. And if one does this cheating procedure, if you know and execute it. Sorry?
The cheating is in quotes?
No, yes. The quotes are around the word cheating in some slide. Yes, it's a technical term. If one does the cheating procedure, in quotes, yes, then one doesn't need to motivate the motivated proof. And the empirical hypothesis isn't empirical. The proof isn't motivated, it's just a push button by cheating. But we want all the input we can get. And there's a lot going on now. So I was supposed to, I love to give graduate courses. I got to give a graduate course, but Matthew Russell was one of the students in it, Durham student, and he is not an expert on vertex operator algebra theory. The 5 other students were in vertex operator algebra theory, and I didn't want to exclude him. So I gave an elementary, in the quotes, technical sense course on motivated proofs. But halfway through the course, I finished the Andrews-Baxter paper and mentioned Jews and my more general thing, and we had a lot of discussion, and I had nothing more to say. That was the end of knowledge. So I suggested we have a collective homework problem, and we tried the Andrews-Berceau even modulus identities would be too difficult. Drew Sills and I had tried to do it, and the hard part was in the motivated proof attempt. You don't seem to be able to divide by pure powers of Q to generate the analogs of those G sub I of Qs. We were forced to divide by things like 1 plus Q to a power, and that wrecks everything. We had a structure, but we couldn't finish it. So I suggested we have a class homework problem to use the second half of chapter 7 of Gordon's book and try to construct a quote, motivated proof of the Goelitz-Gordon-Andrews identities, and it worked. And as I joked before, finally I respected the Goelitz-Gordon-Andrews identities. Before that, they didn't have anything to do with any Lie algebras, so I wasn't interested. But the seven of us did that, and then based on an idea of Kanata and Russell, the two graduate students I mentioned, we were able to, Drew and they and I were able to construct a motivated proof of the even modulus Andrews-Brisou identities by the introduction of something called ghost series, which have the wrong parity conditions. This is the Andrews-Brisou identities where the sum side is in words as opposed to Q series form. And some of you are experts on this, but it doesn't matter. Replace this congruence condition mod 2 on the sum side by not congruent to this mod 2 on the sum side. And that interpolation of these ghost series made everything work. This isn't part of my talk, but I'm going to put this in anyway. It's not part of my talk because when you get talented people interested in things, they go off and do things you don't know what they're doing. So one day, Matthew Russell and Shashank Kanata came into my office and they said, we've discovered some new identities by an experimental method using Maple and ideas. I won't go into it. But here's one of them. One of the ones they discovered, it's only a conjecture. They have a paper online, Identity Finder, that's their Maple program. It's open source. Anybody can push buttons and see if you can discover new identities using your Maple program. I won't say how it works, but if you can prove this, then, well, that's my next attempt beyond Camporelli. Nandi, Drew will write Nandi's identities in his talk to stimulate all of the experts here. This is online. It looks like Camporelli's result, his identity, but it's different, and the product side has asymmetrical congruence conditions.
And it's highly not Taylor.
Well,
George Andrews tried.
right, no, so George has tried, and he gave an entire talk explaining his attempts to do it, which is really amusing. And Matthew and Shashank, he discussed ideas, and it's still unsolved, right? Okay, so in a generalized sense, vertex operator algebra theory is generating output for partition theorists. Now, I have like 2 minutes, I guess. How many minutes do I realistically have, and I'll see how many slides to skip.
I think 2 minutes.
Okay, that's what I thought. So, I also hated over partitions until it turned out that Steve Mill and I had a fudge factor discrepancy between the product sides of Rogers-Ramanujan, Gordon, Andrews-Brisou, and the Q series that came out of the Lie algebra theory. That fudge factor is a technical term. But if you restore Mills and my fudge factor, and that's very appropriate, Steve is here, and I was just saying, this just happened, I'll put it in my talk. If you restore the fudge factor, which was bad then you get over partitions. So that's a new thing for us collectively to do, as more practice. Do motivated proofs for over partitions. One can cheat in the technical sense because Corteil, Lovejoy, Mallet, Chen, Tseng, and Xi have XQ type proofs, but it's more subtle than that because one has to use ghosts and so on, including an undergraduate that Chris Sadowski is already getting involved in this in his new teaching job. Yeah, see, I told you. The word sheet is there, and it's in quotes. It's a technical term. My last point is I told you that there was one boring step. And it's not boring anymore because my current finishing student, Bud Poulsen, has rewritten Min Shenju's and my motivated proof of the Gordon generalization of Rogers-Ramanujan, in such a way that every step and every step in the boring part is now conceptualized by a translation into the language, to the idea of the affine Weyl group for SL2, which is the Weyl group SL2 had. And there's new geometry, new algebra. This will generalize. So this is the last thing I'll say, except for this.
Thank you very much. Very nice talk. Any questions?
Your residual classes 2, 3, 5, 8.
Yeah, you mean Matthew,
The last one.
Kanata Russell?
Yeah. Do you
Yes.
have a theorem for 1, 4, 6?
Well, okay, so,
Yes.
yeah, right. So Russell and Kanata communicate freely with anybody, like George Andrews or everybody we could think of collectively, but they should have emailed you. And any ideas, you know, free open source type research, that kind of research. And I think you said they should look at the opposite mirror, you know, the mirror opposite convergence condition, which is natural. And Matthew pushed his button some more and found more.
It doesn't help.
It doesn't help. It didn't help when George was explaining his attempts to prove either one or both of those together. Like maybe there's a motivated proof that connects the two of them. I mean, there are all kinds of crazy ideas that you use. And then the goal is for some sort of new motivated proofs to give new ideas about twisted intertwining operator algebras. That's what I really want.
Any other questions? Then let's thank the speaker again. And we will resume again very soon, in 3 minutes or so, because there will be a long break afterwards.